Hello folks, and welcome back. Today we're going to be covering the fundamental theorem of algebra. Now you know this is going to be an important lesson because it's the fundamental theorem of algebra. It's the fundamentals of everything that we've been discussing so far this year. Let's go ahead and start to think about some things, and then we'll get into it. Now, what are the number of possible real solutions or roots that a quadratic can have? Remember, your solutions or your roots are the same thing as your zeros. So what are the numbers that we could have? And then how do we justify this using the concept of graphing? So the total number of roots you could have 0 roots. This is going to happen if we have no x-intercepts or no roots, never crosses the x-intercept. We could also have one solution or one root. This happens when we just touch the x-axis, but we don't go through it. And finally, we can have 2. This is what happens when we cross over the x-intercept twice. Now, today's lesson, we're going to be solving polynomials, so we need to cover all of the different ways we have learned to solve a polynomial. The first one we have is factoring. What are the pros we have for factoring? It's quick and it's pretty simple. What are the issues? Well, not every polynomial can be factored. So we can use factoring because it's quick and simple, but it won't work every time. One of the other tools we have is graphing. What are the pros? Well, it can be done with a graphing calculator, so it takes some of the work off of us. And I also find that it's pretty quick and simple as well. Now, what are the issues with graphing, solving by graphing? Well, it can't tell us precise answers for irrational numbers. So it can't give us exact irrational solutions. And it can't give exact imaginary solutions. It can't give imaginary solutions at all. What about completing the square and quadratic formula? Well, these two work for any quadratic that we have. What are the issues with it? Well, it can be long to do it and it can be difficult to do. Okay, so far we've covered factoring, graphing, completing the square, and quadratic formula. Next we have u substitution. Now this isn't one we've talked about, but we'll see an example of it. All this means is if we have something that looks like x to the fourth plus 2x squared plus 3, we can say that this looks like some sort of equation that's quadratic, as long as we say that u is going to be x squared. So by simplifying this so that we're looking at only x squareds as our variable, this becomes a quadratic. So what's the pro here? It makes things that aren't quadratic look quadratic. Okay, what are the downsides? Well, it can be confusing, like we've just seen up here, and it doesn't work every time. It doesn't work on every polynomial. Okay. This leads us into our next one, which is the real roots theorem. The real root theorem tells us all possible solutions, or integer or rational solutions. The issue here is that it doesn't tell us which of these possible solutions are solutions. Remember, the rational root theorem is where we take the constant or the factors of the constant and we divide it by factors of the coefficient. So this is the one where we have factors of the constant divided by factors of coefficients. The other issue we have with this is it tells us about the integer or rational solutions. It doesn't tell us anything about the imaginary or irrational solutions. Next we have p of k and remainder of 0. This is the one where we said that if we sub a value in and it equals 0, then it's a factor. The good part about this is it tells us which of our possible solutions are solutions. So it tells us which the possibles are. The downside to this, though, is that there can be a lot of different things to try. So these are the 6 different ways that we have for trying to find answers for a polynomial. Let's go over them again. We have factoring, right? It's very easy, but it doesn't work all the time. We have graphing, which we can just throw into our graphing calculator, but it doesn't tell us about imaginary or irrational solutions. We have completing the square and quadratic formula, which works excellently with quadratics, but it can be long and hard to use. And if we don't have quadratic, it's not useful. We have use substitution, which works only some of the times, but it allows us to look at things and consider them more or less quadratics. We have the real root theorem, which tells us all of a list of possible solutions, but it doesn't say which ones are solutions, and we're still left without irrational or imaginary numbers. And then we have the testing of the real root theorem, which says which ones are solutions, but it can take a long time. Now that we've remembered all of these tools, we're just going to be like a handyman, trying to find the right tool for the job when we're trying to find solutions. Before we get to that, though, we're going to cover the fundamental theorem of algebra. This was found, for a short tangent, by Carl Friedrich Gauss, or I'm just going to write Gauss here. Gauss is a very important figure when it comes to mathematics. You'll see his name pop up everywhere as you continue further on in math. But what this theorem says, it's really actually sort of simple to think here. For any polynomial with degree n, and that has to be at least 1, we have n roots, including multiple and complex roots. Or in other words, if you have a polynomial of degree 7, you're going to have 7 roots total. That includes multiples, complex, and irrational roots. So let's go ahead and use some of this to practice. Oh, one more thing, a side note. If a polynomial doesn't have a constant term, then we know that 0 is going to be a root. So keep that in mind. Now let's move on to an example. We're trying to find all the roots of x to the 5th minus x to the 4th minus 3x cubed plus 3x squared minus 4x plus 4. The first thing, let's consider the fundamental theorem of algebra. It says that if we have a polynomial of degree n, in this case n is 5, that means we'll have 5 roots. So we have a total of 5 roots we're looking for. Now how are we going to find these 5 roots? Go back to your toolbar. Tell me, what are the methods that you would use to do this? Now if you said graphing, that could work. If you also said the rational root theorem and the remainder theorem, those are what we could use. We couldn't use u substitution. We couldn't really factor this as we see it, and we definitely can't complete the square or use the quadratic formula. So let's go ahead and start with the rational root theorem. What are our factors of the coefficient? It's plus or minus 1. What are our factors of the constant? It's plus or minus 1, 2, and 4. This means that our possible roots are going to be plus or minus 1, 2, and 4. We have our possible roots. Now we're going to go ahead and try to solve this. So first thing we're going to do, let's test a root out. We're going to test 1 and see if that's going to be a root. So that's going to be 1 to the 5th minus 1 to the 4th. Remember, we're just subbing 1 in for x in this equation. Minus 3 times 1 plus 3 minus 4 plus 4. Put that into our calculators. We'll see that that is equal to 0. What does that mean? That means that 1 is a root. So let's go ahead and divide that root out. Right? This was the whole part about finding the zeros and dividing them out. So we have 1 here, and we're going to write our coefficients. 1, negative 1, negative 3, 3, negative 4, and 4. We're going to synthetically divide these. So we end up with 1. 1 times 1 is going to give us 1. Add those together. Multiply that to 1. Keep adding and multiplying. So 1 times negative 3 gives us negative 3. 3 plus negative 3 will give us 0. And we'll get 0 plus negative 4 and 4 plus negative 4. Okay. What does this leave us with? Well, we have our term here. Remember, when we're synthetically dividing, if 1 is a root, that means that x minus 1 is the factor. We have to flip the sign there. And what are we left with? Well, we have, let's see, we start with our constants, right? This 0 is our remainder, so we have constants, linear, quadratic, cubic, quartic. So we have an x to the 4th term, we have 0x cubed, we have minus 3x squared, and we have minus 4. So we found one of our roots. Now we just need to deal with x to the 4th minus 3x squared minus 4. This is our example of u substitution, right? We see this, we have x to the 4th and we have x squared. So if we just say something will be equal to x squared, all of a sudden what we have is something that looks like a quadratic. We have u squared minus 3u minus 4. So by looking at this, instead of as x squared, we just substitute something in. We have something that looks quadratic, and we can just factor this. Right? So if we do that, we're looking for factors of minus 4 that are going to add up to minus 3. What is that going to be? That's going to be negative 4 and positive 1. So that means that this will be u minus 4 and u plus 1 is equal to 0. Or we know u is x squared, so we're just going to replace those u's with x squared. X squared minus 4 times x squared plus 1 is equal to 0. What does that tell us? It tells us that x squared will be equal to 4, and x squared will also be equal to minus 1. So when we take the square root, what are our solutions going to be? Well, square root of 4 is going to be plus or minus 2, and the square root of -1 is going to be plus or minus I. So our roots are going to be, we had 1 from our test. We had plus and minus 2, so positive 2, and negative 2 from x squared is equal to 4. And we had positive I and negative I from x squared is equal to -1. So all we're doing now, we're looking for all of the roots using whatever tools we have in our toolbox. We're just going to be little carpenters here. All right, now let's move on to this next one here. We're trying to find the roots of x to the 4th plus 2x cubed is equal to 13x squared minus 10x. What's our first step here? Well, we need this to be equal to 0, so let's go ahead and start there. So we're going to change this to x to the 4th plus 2x cubed minus 13x squared plus 10x. Now here's the next question. How many roots are we going to be looking for here? Well, our degree for this is 4. We have x to the 4, meaning we have 4 roots. It's just as simple as that. Now, what is our first step? What tool should we use first to start solving this? The only correct answer here is to factor. Notice how we don't have a constant, meaning we can pull out an x. Remember, that also means, we set up here, if a polynomial does not have a constant, then 0 is a root. So let's pull out x and let's make that one of our roots. So we're going to factor. I'm going to pull out that x. We're left with x cubed plus 2x squared minus 13x plus 10 is equal to 0. And this tells us that 0 is a root. Now, what tool should we use next to solve for x cubed plus 2x squared minus 13x plus 10? The correct answers here are either graphing or rational root theorem. Let's use rational root theorem though here. So we have our factors of the constant are plus or minus 1, and our factors of 10 are going to be plus or minus 1, 2, 5, and 10. Now we're going to divide the numbers on the right by the numbers on the left, meaning our possible roots are just going to be 1, 2, 5, and 10, positive or negative. Now we're going to test all of these out until we find one that works. Let's test 1. When we do this, we're going to get 1 plus 2 minus 13 plus 10. Remember, we're just subbing this in, and because we're only trying to solve for x cubed plus 2x squared minus 13x plus 10, we just need to sub it in for x in that part. When we do this, what do we get? We get 3 minus 13 plus 10. That's equal to 0. So what does that mean? That means that 1 is also a root. So 1 is a root. What's our next step? We're going to divide 1 out using synthetic division. So we're going to take 1 here, and what are we left with? We have x cubed plus 2x minus 13x plus 10. So we're going to use 1, 2, minus 13, and 10. Let's see where this gets us. So we pull down the 1, we multiply it. That gets us to 3. We multiply that. Negative 13 plus 3 is going to give us negative 10. And that'll get us to 0. So what does this mean? It means we pulled out an x to start. 1 is our root, meaning that our factor, right, we have to flip the sign, is x minus 1. And we're left with x squared plus 3x minus 10. Okay. So we know 0 is a root from this. We know 1 is a root from here. We just need to solve x cubed, or x squared plus 3x minus 10. How are we going to do that? If you said quadratic formula, completing the square, graphing, or factoring, those would all be correct. Let's use factoring though, because this should be quick and it should work. We're looking for factors of negative 10 that are going to add up to be positive 3. That'll work if we have 5 and negative 2. So that means fully factored, this is going to be 0, or x times x minus 1 times x plus 5 times x minus 2. And what does that mean our roots are? Our roots are going to be 0, 1, x plus 5 is equal to 0 will give us negative 5, and x minus 2 equals to 0 will give us positive 2. Now here's a question for you. How many x-intercepts did each of these equations have? For this example 2, x to the 4th, we had 4 different roots. But for example 1, where we had x to the 5th, we were expecting 5 roots, we only had 3 x-intercepts. What this goes to show us is some of our intercepts could be imaginary or they could be repeated. So make sure we keep that in mind as we go ahead and do this. We have a couple more examples here. This one we're going to be using our solving by graphing abilities to begin this, and then we're going to find all of the zeros. So go ahead and graph this. Tell me what appears the zeros will be. So here we are. We've thrown the equation into our graphing calculator. Let's give it a good old standard zoom. Make sure we're looking at the right area to see what it looks like we have. Looks like we have zeros at -3 and +3. Let's double check these though. Remember how we double check? We're going to hit second. We're looking for calc, so we're going to hit trace, and we're looking for a 0. Once we get there, it'll ask us for a left bound and a right bound. You want your left bound to be left of where you think the answer is. So in this case, we want it to be left of -3. It's left of our answer. We'll hit enter. It'll ask us for a right bound. So we want a number to the right of where we think it'll be. And then for a guess, we put whatever we think our answer will be. And it looks like -3 is a 0. We'll just assume 3 will also be a 0 as well. So what's our answer here? By graphing, it appears that -3 and +3 are zeros. Let's go ahead and divide both of those out. So now we're going to divide both out. Let's start with +3 here. We have 1x to the 4th, 1x cubed, minus 7x squared, minus 9x, minus 18. So we're going to go ahead and do this. We get 1. 1 times 3 is going to give us 3. 1 plus 3 is going to give us 4. Now 4 times 3 is going to give us 12. -7 plus 12 is going to get us to 5. 5 times 3 is going to give us 15. -9 plus 15 is going to give us 6. And 6 times 3 is going to give us 18, which gets us to 0. So we factored out the 3. What we're going to do is we're going to use these values here. So all of the numbers from our division for the second time. Because we already factored out the 3, we're going to factor out the -3 as well. So to factor out the -3, we're going to pull in 1, 4, 5, and 6, as opposed to our original values, because we already factored out the +3. Let's go ahead and do this. We pull down the 1, multiply it by -3, add those together. Multiply it by -3, add those together. Multiply it by -3 and add it together. So what does this mean? We factored out x plus 3 and x minus 3. Remember, we flipped the signs. So the 3 will give us x minus 3. The -3 will give us x plus 3. And what are we left with? We're left with x squared plus 1x plus 2. Now, how are we going to solve this last part here? We can do graphing, we can do quadratic formula, we can do factoring, whatever you want. Now, if we try factoring, we're looking for factors of 2 that adds up to +1. And that's not going to work. So it looks like we're going to have to use quadratic formula. Let's go ahead and get to that then. So we're looking for x is equal to -b plus or minus the square root of b squared, so 1 squared minus 4a, which is 1c, all over 2a. That's going to be, let's keep simplifying, plus or minus the square root of 1, and we have minus 4 times 2, so minus 8 over 2. When we keep simplifying, right, 1 minus 8 will give us minus 7. The square root of minus 7 will be 7i. So this is going to be negative 1 plus or minus 7i over 2. What does this mean our roots are? Our roots are going to be positive 3, negative 3, and our two roots are negative 1 plus or minus 7i over 3, or over 2. So that would be negative 1/2 plus 7 over 2i, or we can write it fully divided out, and negative 1 over 2 minus 7 over 2i. Right. We have one last one here. We're going to think through this a little bit. We have the graph of x to the 5th plus 4x to the 4th minus 3x cubed minus 12x minus 4x squared minus 4. Lot to say there. Here's the basic graph. We're going to use turning points to explain why the graph does not show all the real zeros of the function. So looking at this, how do we know that we have at least one more zero? How many turning points do we have? We have 1, 2, 3. Now what's our degree here? It's degree 5. Because of that plus or minus theorem that we talked about on Friday, we know that we need to have at least 1 or 3 or 5 zeros, right? We can't just have one imaginary zero. We need plus and minus. So that means we're going to have to turn 0 times, or 2 times, or 4 times. So why can't we have just these be the zeros? Well, because we need 4 turning points, or 4 turning points. So what's our answer for this? For 1, we can say that imaginary zeros show up in 2. Right, this is because of the plus and minus theorem. Additionally, if we look at this, we have x to the 5th, where our end behavior for an odd function acts like a cubic, right? So we expect these to go in opposite directions. The way it is, it goes up and up, and that's for even functions. So we also can look at the end behavior. The second problem, it says the graph of g of x is f of x plus 4. It's a translation 4 units up. How many real zeros will this have? Well, if we move this graph up 4, what do we expect to see? See, if we move this up 4, we would have some sort of zero in here, but we'd also move through because this would move up. We'd move through up here, and we'd move through again. That means we'd have at least 4 zeros. But what does that mean? We know that imaginary zeros show up in 2s. We need a plus and a minus. We only have one more zero we can do because this is degree 5, so we only have 5 zeros. So this means that we have 5 zeros together, or 5 real zeros. Imaginaries are going to show up in 2s, so we know we need to have all 5. And that, folks, is all we have. Remember, this lesson is all about becoming a handyman. The fundamental theorem of algebra just tells us how many zeros we're looking for, and then it's up to us to use the right tools for the job. Anyways, go ahead and get started on your homework.